We are now recording. I wanted to put the last couple of announcements on, there we go, Screencast-O-Matic, so ultimately they'll be on YouTube so everybody can hear them. I was wrong last week when I was telling you last week was the end of first mini-term and this week was the beginning of second. It wasn't quite true because I found out since then Monday of this week was the last day of first mini-term, and Tuesday was the beginning of second mini-term. So that means that, not that it's a big difference, but it's just to let you know that the, got that. The reason I say that is usually the week after midterm, which was around midnight Tuesday, Monday night, Tuesday morning, would have been the time I think they usually say, now is the time to do midterm progress reports. I'm going blank on the name. Midterm progress reports. Okay. Alexis? Okay. All right. And as far as I know, they haven't opened those yet. But they could open them anytime this week. And at that point, I'll have to put down people who have D's or F's at midterm. Now, right now, this class has 5. My biggest class, 5 students who have turned in a paper. Now, that's not bad, but we could do better, okay? And now Amber Jones, okay? The first test, the first quiz, 3, 4, 5, 6 people have, well, one of them withdrew. So 5 people haven't turned in the first quiz, okay? And many of those didn't do a paper either, so that means you haven't done the test either, because I've had only 6 people complete the test, or at least as far as I know. Now, if you've completed the test, but you don't see your grade on Blackboard, that means I wasn't sure if you're complete or not. So please let me know if you are finished or not, or if you're going to complete it, come on in and get that done. And this is Brianna, right? Okay. All right. So I do need to have some sort of grade in this week or Monday, okay? So that means you got today, you got tomorrow. I'll be on Birmingham campus. Now, if you don't want to go over there, you can slide it under my door. If you're going to be on this campus, I'll pick it up Monday, and then I'll get it graded and entered. Or get it to me sometime Monday. I know we don't meet until Tuesday, but try to get me something. Your paper, your quiz, or get working on your test. Okay. The one other thing, I think I announced this before, but just to make sure everybody understands, my office hours changed at midterm because my second term physical science class doesn't start until 1:15. The first mini-term started at 12:30. So that means on Tuesdays and Thursdays today, and all Tuesdays and Thursdays, my office hours are 10:45 until 1:15 now. Longer than they were before, 10:45 to 12:30, now 10:45 to 1:15. Of course, that also means I'm here later in the evening. I leave, my class gets over at 5:45, and I leave around 6. So you can catch me then if you're around. All right, any questions before we get started on today's material? Okay, where we left off last time was talking about leading coefficient tests, and what this pertains to are polynomials generally of higher degree. But they work for polynomials of lower degree, it's just those are usually pretty easy. Okay, so if you have a polynomial of fairly high degree, degree n, whatever that is, 3, 7, 14, whatever, if that's your degree, then for the end behavior means what happens in the long run. Very large negative x's, very large positive x's. Doesn't affect, it affects, but the stuff in here affects the stuff that's happening in the middle, okay? But in the long run, this term is the one that dictates what happens. Okay. So in this first term, that n is odd. That means in the long run, your on one side, your function is going down, on the other side up. Because with polynomial functions, you're going to be heading to infinity in both directions, or in one or the other directions. With an odd exponent for your leading term, those are going to be opposite directions. Okay? Next one. Okay. Now, again, it doesn't tell you what's happening in between, but what happens there. And here's how they write it. And you'll be required to write it. As x approaches negative infinity, your f of x is now approaching negative infinity. Okay? As x approaches positive infinity, your f of x, your y, is going to positive infinity. That's how you write and indicate in behavior. Now this is when n is odd, and when the leading coefficient is positive. Okay? So you see, it's not just the leading coefficient, it's the whole leading term. The n is on the exponent of the variable, the coefficient is here. So if you got an odd degree on your leading term, you know they're going opposite directions. Well, which way are they going? If the a is positive, then when x is negative, that's going negative. X is positive, that's going positive. But when a is negative, it flips everything. Okay? And then when x is going negative, f is going positive. And x going positive, f is going negative. Okay? And this is how that is represented. As x goes to negative infinity, your f of x or your y is going to positive infinity. As x goes to positive infinity, your f of x is going negative. Because this negative a flips and makes that happen. Now, these are a lot of words, and the concepts are hard. Let me get it down. But if you don't like memorizing rules and things like this, here's what I suggest. If you have a polynomial, pick a big x, and it doesn't have to be very big, especially if this is a high-degree polynomial, like 10. Okay? Now, give me an n, something greater than 2. 3, okay? Can't get much less than that, greater than 2, right? Well, if you take 10 and cube it, 10 to the third power, what have you got? 1,000. You're going way up there. Now, if this is a negative number, that makes it negative 1,000, or whatever that number is, multiplies it by. So you're going downhill fast. So you see, you can just take a, not that huge of a number, you're nowhere close to infinity, and then take a negative 10. And again, if this is odd, what happens to a negative 10 if you raise it to the third power? Negative 1,000, okay? And if this a is positive, it's going down. If this a is negative, that's going up, okay? Because it changes the sign. So if you don't like remembering these rules, just plug in a number like 10. And look at your leading term, see what happens with a 10 in there. And then do a minus 10. Positive 10 tells you what's happening this way, negative 10 that way. Does that make sense? Okay. Here we go. Now, what if the n was even? Those are all odds. What if n is even? What's happening to your function then? Let's first take for the a being positive. You take everything's going to be positive. It's on the up and up, right? Because if you take a negative number, like negative 10, and raise it, okay, give me an even number greater than 2. 4, okay? You pick the lowest one again. Well, negative 10 to the fourth power is 10,000. That's pretty big, don't you think? And positive 10 to the fourth power is 10,000 again, okay? So it's on the up and up, unless the a, that's if the a is positive. If the a is negative, then it flips them both down. Make sense? Okay. So that happens on n is even. They're going the same direction. It depends on whether a is positive, then they're on the up and up. If A is negative, they're heading down. Does that make sense? And here's how we express it. As x approaches negative infinity, f of x is going to positive infinity if the A is positive. And if as x approaches positive infinity, the f of x is still going up if this is an even n, and the A is positive. Okay? So that's approaching positive infinity there. As x approaches negative infinity here, when A is negative but n is still even, then the f of x is going down, and as x approaches positive infinity, the f of x is going to negative infinity. Now, I want you to notice something, because you will be filling in the blanks here.
So we'll need to know how to write it out.
I will write out as x goes where, what does alpha of x do? As x goes where, what does alpha of x do? I'll write that out and you fill in the blank. Now I want you to tell me what you notice about all those blanks. Every one of them. The thing that follows the arrows here. They're all some type of infinity, aren't they? So do that to begin with, okay? If you have those blanks there, it's asking you what to do, then the answer is you mark Terrell here, okay? And at the same time, you mark Ryan here. If I can keep you on the right track here. Okay. Good deal. We're doing top of page, well, basically all page 126 here. So if you have the question and looking for end behavior, then you're going to have, as x is doing this, blank, f of x is doing blank. As x is doing blank, f of x is doing blank. Okay? And notice what goes in every blank in any situation is an infinity. Go on and put the infinities down there, okay? Put them down, okay? You have a 50-50 chance of getting all of them right then, okay? No, don't get the 50, okay. Now, for the x's, notice, one's going negative and one's going positive. One's going negative, one's going positive. One's going negative, one's going positive, one's going negative. So you can put your x's as x goes negative infinity on the first one, positive infinity on the second, or vice versa. I don't care. Just make one a positive, one a negative. And then all you have to do is figure out what signs goes with the f of x. It's either going to be plus plus, negative, minus minus, plus minus, or minus plus. Okay? And even if you don't know what you're doing, you can make a guess. Okay? So please don't leave those blank. Please don't put x going to positive infinity twice. One's going positive, one's negative. Now, the y's, the alpha of x, they could both be going the same direction. Okay? You have to figure that out. But you know already all four blanks are going to have an infinity in it. Two of the x's, one x is going to have a plus and one's going to have a minus. Okay? And then you figure out the sign for the y. That's all there is to do for the alpha of x. Okay? Now, like I said before, the dashed portions of the graphs indicate that the test determines only end behavior. The leading term test tells you only end behavior. Those other terms in there, they determine all this wiggle and squiggle that's going on there. Okay? Or just the humping or whatever. Any questions? All right, let's do some. Describe the right hand and left hand behavior of the graph of each function. What do you reckon this is doing? And guess what? All right, Justin's here. Have I missed anyone when you came in? Okay. All right, I'm going to, well, why? Oh, there it is, finally. Okay. Get my pen darker. All right, I'm going to show you what it'll look like on the quiz or test. Say again? I can't hear you say again.
Which one would be considered end?
Okay. Well, I'll get to that in just a second. Great question. Let me write these down. This is example 2 on the top of page 127. Okay, yeah, good question. What is your N? Anyone give me an answer to that? Okay, the largest exponent. That's the answer, the largest exponent. Here it's going to be 3, here it's going to be 4, yeah, I thought, okay, here it's going to be 5, yeah. The largest exponent, that's your N. That's what you use to determine. Yolanda's here. Pardon me? Oh, okay. Okay, and this is what you're going to see on a quiz or a test. You tell me what to fill in the blanks. Okay, you can start with negative infinity as you want. Really? Let's just put in our infinities. We know infinities are going to go here, and you determine the sign. You already told me that's a negative. That one then has to be positive. Okay? Now, what can you see here? Odd exponent, that means they're going opposite directions. But the negative coefficient means they're going opposite of what you would think they would go. Usually negative goes negative and positive positive for odds, but since the negative exponent, they go like this. Feel like I'm doing semaphore. Okay, no. Negative. So this would be going positive infinity. Leave that one alone. You know that x goes to positive infinity, since you chose negative first, that's going to be positive here. Then what is your F doing? It's going negative because it's going the opposite direction because it's an odd exponent. You got it right. Okay? So this is going to be as x blank, f of x blank, x blank, f of x blank. Okay? What goes in every blank? An infinity. Put them in. You know that it's going to be an infinity. Now this is for polynomials. Polynomials. Later when we do rational expressions, we'll have different things going in there. Okay? But for polynomials, they're all going to be infinities. And how about the x's? One's going to be negative and one's going to be positive. We got those. Guess what? You know you got 2 right already. There's a good chance you got 1 of the other 2 right. Okay? Take advantage of every point. Okay? Now, on this one, what's happening? Second one? Okay, because it's an even exponent. In what direction are they going? Positive, because it's a positive coefficient. You got it. We got the answer right there. You see? See how it works? Okay. Let's do this one. As this goes blank, this goes blank. As this goes blank. Sorry about that. Put the blank in the wrong place. Oh, it didn't erase. Okay. Okay. Comma. Okay. What goes in every blank? An infinity. For polynomials, it's an infinity. May not be for other things, but for polynomials, they are. And what about your x's? One's negative, one's positive. Okay, we got those. You know you got 2 right so far. Okay? Now, what is this one here? Okay, because you choose the x, one to be going negative and one going positive. You don't want to choose them both here, they have the same answers. You want in behavior, left hand, see, right hand and left hand. Now, if you want to do it in that order, you'd have done plus, 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 and minus, minus, minus. Okay, that's what that is. And one's got to go to the right. Now, and the others have got to go either up or down, but that's what you got to figure out. Okay, so what makes your determination here? Odd power tells you what? They're going opposite directions. So those 2 signs are going to be opposite for the F's. Okay. Yes, you got that right. The left is going down. If you put, and here's my other technique for those who came in later. If you can't remember what to do, now only focus on the leading term. They like to call it leading coefficient, leading term. Pick an x, a positive 10 for this one. 10 cubed is 1,000. Negate that. A negative 1,000. As x goes positive, this is going negative. You see? Okay, pick a negative 10. Negative 10 cubed is negative 10, negative 1,000. Then when you negate it, it's positive. So as x is going negative, like negative 10, your alpha is going positive. So that's the other way you can do it. Plug it. Let's do this one that way. Choose x equal 10. 10 to the 5th is 100,000. That's pretty high, isn't it? Okay? As x is positive 10, this is going to positive 100,000. That's going to be a plus plus. Okay? And if x is going to negative 10, that's not even near infinity, but negative 10, what's negative 10 to the 5th power? Negative 100,000. So if x goes negative, this one also goes negative. You see how that works? Okay? Other little hints, maybe. If this is odd, these two f's are going to be opposite signs every time. If x is even, these are going to be same signs. But that doesn't tell you what the signs are, but they're going to be the same. Does that make sense? This should be pretty easy. Those should be give me points, right?
So you said when x is even, they're going to be the same?
Yeah, when x is even, the f's are going to be the same. X's are going to be plus and minus, but the f of x is going to be same sign. If x is, if the n is even, yeah, the exponent is even. Huh? Okay. All right. Let's erase my chicken scratch here and see how they do it. Okay? The first one. They draw it. Oh, we should have thought of that. That's so easy to draw, right? I think it's so much easier to look at them. Because the degree is odd, but the leading coefficient was negative, this is going, when x goes negative, this is going positive. When x goes positive, this is going negative. Okay? Now, I don't know if they even wrote them out. They just drew it. Yeah, they didn't write out the answers. On the test, you'll need to give me answers, not just, if you want to draw a figure, fine, knock yourself out, and you show me on that what's going on, then that's fine too. Okay? All right. The B one was this one. Even exponent, positive coefficient, it's on the up and up. As x goes negative, y is going positive. As x going positive, f of x is going positive. Make sense?
So, okay, question. So, exponent, the coefficient is even, so that means it's...
Okay, no, coefficient, okay, this is the exponent, that's the coefficient.
Yes, so,
Yeah.
Since the coefficient is odd,
Okay. Exponent.
exponent, since the exponent is odd, that means it's going to be negative.
Well, that means one of the other is going to be negative because they're going opposite directions. Okay. On this one, the coefficient, you got me doing it now. The exponent is even.
So when the exponent
So
is
it's going
even,
the same
y
direction.
is going to go the same direction.
Right. The f of x and y is going to go in the same direction, and it's going to go in the direction of your coefficient.
So
That's
since
positive, so
the
that's both
coefficient
positive.
is odd, then...
No, exponent odd.
No,
Now, the coefficient is whether it's positive or negative. Exponent is whether it's odd or even.
whether it's good, the coefficient is good.
The coefficient, well, all that matters there is whether it's positive or negative.
Oh, it's not
The
even
exponent
odd.
is even and odd.
Oh, okay.
Yeah, that's easy.
Okay, so since it's
Let me
positive,
mark Jeremy before I forget he came in. Okay, there he is. Okay.
so coefficient is whether it's even or
Exponent is whether it's even or odd. The exponent, the raised little number there,
okay.
that determines, that you look for even and oddness. Those are always positive. Exponents are always positive. If this is a polynomial function, the exponents are always positive. So what you look for there is even or oddness. The coefficients, they can be anything. What you're interested in is whether they're negative, positive or negative.
Since it's positive, it's going up.
Okay, if it's even exponent, you know they go in the same direction,
Right.
either up or down. If
Direction
that's
of
a
the
positive exponent, it's going in the direction of the coefficient. Exactly.
Okay, so if it was a negative x, then in a positive exponent, then that means that
Right. They're all
going-
positive exponents.
Okay, even. I meant to say even.
Okay.
Even. So if it's so if that number is 4, but then the x was negative, then they will all be going to the negative.
Yes, exactly.
And if
The F's will.
yeah, the x will be going to
The
negative.
X's are always positive, one positive, one negative.
Yeah. So okay.
Got it? Good deal. I think you got the concept. It's just getting the words to come out right. Okay, let's look at the number C. Number C, what do we have? Odd exponent, positive sign. So, as x goes negative, alpha of x goes negative. As x goes positive, alpha of x goes positive. Now, I'm not saying infinity every time, but that's what you do. As x is going to negative infinity, alpha of x is going to negative infinity. As x is going to positive infinity, alpha of x is definitely going to positive infinity.
Okay, I have to.
Sure.
Okay, since the exponent is odd,
Right.
so we know one's going to go to positive
And one's going negative.
How do you know which one's going to go positive?
Okay.
and which one's
Then you look at the coefficient again. If that's positive, positive goes positive. If that's negative, and odd exponent, negative goes negative. But if this coefficient is negative, it flips both of them. So a negative x goes to positive y.
Okay,
And a
explain
positive.
it.
Okay. If you have odd exponent, they're going in opposite directions. Okay. If the coefficient is positive, you go in the same direction of the sign here. As x goes positive, that goes positive. X goes negative, that goes negative. Okay. If it's an even and odd exponent. If the odd exponent but a negative coefficient, that flips everything. So positive x is going to a negative, so alpha of x is going negative. Because the negative there flips it across reflects across the x-axis. Okay? And then as x goes negative, this will go positive. So that makes it go in the opposite direction from the direction of x. Okay. All right. And again, just plug in plus 10 and minus 10 and see what you get. Plug in a plus 10 here, plus 10 to the fifth is positive 100,000. That's positive, okay? A negative x here, raised to the fifth power, is negative 100,000. That's what a negative is. Okay. Good deal. All right. Now, in that example 2, and by the way, there is a checkpoint here. I'd say good thing to go home or right after class or somewhere and do those checkpoints. Now, I meant to say this earlier, and I'll say it now. My work-study student is also a math tutor at the Space Center down on the first floor. He's really good, okay? And he said most days he's sitting down there getting paid, and you don't pay him. His college pays him. It's on a federal grant, okay? He's sitting down there not helping anybody. He said, I want to have someone come in. So if you need help with any of this, he is good. Now, SSS math, right down the hall here, up on the second floor, 20, I think the room down there for Space Center, I believe, is 105. I'm not sure. I believe that's right. But here on the second floor, the Student Support Services tutoring program, excellent program. They're at room 212, I believe it is, 212, okay? If you go out and look down the hall, you'll see 2 exit signs, and there's stairwells that go down on that side. 212 is opposite the stairwell on the right, okay? Great program there. I know at least one math tutor there, Brittany Terry. She is really good too. So you can't lose either place you go to. And both of them are free. Take advantage of them. Like I said, Cameron's down there saying, please send me some students, He gets really bored sitting there, okay? His hours are in the mornings, I think on Monday, Wednesdays, but maybe Tuesday, Thursday too. I know one day he has an 8 o'clock music class, so whatever day that is down there. I know he's in that class, but I think after class he goes tutor. And the other days he's free all day, I think. I mean, not all day, but all morning. Okay. So, but I know there's good math tutors at both places. Now, they're not there all day long, but I bet you they have other good math tutors there when those students aren't there, because they do recruit and get really good students. So, I meant to say that at the beginning. I just thought of it. So, in example 2, note that the leading term test, I don't like the leading coefficient test, tells you only whether the graph eventually rises or falls to the right and to the left. That's what it tells you. Now, this is for polynomial functions. Other characteristics of the graph, such as the intercepts. What intercepts do we have? Y-intercepts, how many of those do we have? Say again? Y-intercepts? One and only one. Okay, and for polynomial functions, you always will have one y-intercept. Now, when we get to rational functions, you may not, but in polynomial functions, you are always going to have one y-intercept. Why is that true? Because polynomial functions are smooth and continuous. There's no gaps, no breaks, so it's got to cross that y-axis somewhere. But it only crosses it once. Why? The y-axis is a vertical line, and it can only cross. It's a function. It can only cross the vertical line once, and it will. And what's the other kind of intercepts we could have? X-intercepts. And how many of those could we have? Say again? You could have 7, or you could have 9. Okay? Now, what do I mean by that? This one had how many? 3. This one had 4, but only had one y-intercept, right? This one had 3, but only one y-intercept. And by the way, the y-intercept and the x-intercept, one of the x-intercepts was the same point, 0, 0. Okay? How about that one over there? It's going this way. It's going to have 2 x-intercepts, 1 y-intercept. How about this? No x-intercept, because it's going up and never crosses the x-axis. Okay? But it will cross the y-axis eventually. Guaranteed. Okay? So you could have 0 x-intercepts, 1 x-intercept, or many x-intercepts. Okay? All right. Then you also have points of interest that are your maximum and minimum points. So we got to figure out a way to first figure out whether it's got any, how many it may have, and then where they might be. So we got a little bit of work to do. But it's going to be fun. Okay. So what we're going to do now is look at real zeros of polynomial functions at the top of page 128. It can be shown that for a polynomial function of degree n, you know what that means? What's that n? An exponent? Which exponent? The highest, the maximum exponent you have. That's degree n. The following statements are true. Okay? The function has at most n real zeros. So if you have a polynomial function of, give me a degree, make up a degree. 5. The most number of real zeros you have. And by the way, real zeros are x-intercepts. Okay? Most number you could have? 5. Okay? Let's go back and look. Okay? This was a 5th degree function, but it only has 3. It doesn't have to have 5, but it can't have more than 5. This was what degree? 4. How many zeros does it have? 4. It can't have another one. You can go as far as you want. It's never going to cross the x-axis again. Okay, this one is a 3rd degree. How many intercepts? X-intercepts? 3. Don't look for any more. That's all that she wrote. Okay? Now, they didn't give degrees on that, so you can't say. I'll wait a minute. Okay. So first, we know the most number of real zeros, whatever that n is. the maximum exponent. Number 2, the graph of f of x has at most n minus 1 less than n turning points. So turning points is also called a relative minimum or a relative maximum. That's when it changes directions going up to down or down to up. Those are turning points. And those are points in which the graph changes from increasing to decreasing or vice versa. That's why we talked about them before. How many turning points do you see here? How many turning points? Say again? Turning points. Here it's going up, up, up. It turns and goes down. There's one. Going down, down, down. Doing a ring of fire or something like that. And then it turns and goes up. That's 2. That's all we see. Okay? If it only has 3 zeros, it can't have more than 2 turning points. Okay? Real zeros. Okay? I may have not said that right, but we'll get there. How many turning points you see here? 3. What was our degree? 1 less than that is 3, sure enough. Okay? Oh, I know what you were doing. Back up. I realize. You said this could have up to 4. It could have up to 4. It doesn't have to have 4. It only has 2. Okay? Sorry. Now I see what you were doing. Okay? How many could this have? Up to 2, how many does it have? 2, yeah. Okay? How many turning points does that one have? 1 and only 1. Okay? How about this one? 3. 1, 2, 3. Exactly. Okay? So, the minimum n for this one would have been 2. It could be 4, 6, 8, or whatever. It has to be even. The minimum n for this would have to be what? 4, because it has 3 turning points. It's got to be at least an n of 4. Okay? Good deal. How about this one? How many turning points? 1, 2, 3, 4. So what's the minimum n? 5. How many here? 2. What's the minimum n? 3. It could be 5, 7, or 9. Yeah, but whatever. Okay, good deal. Okay, so finding the zeros, we figured out how many you might have. Finding them is one of the most important problems in algebra. So we're going to start the process of doing that. But before we do, here's the strong interplay between the graphical and algebraic approaches to this problem. So let's tie them together, okay? Real zeros are polynomial functions. If f is a polynomial function, and a is a real number, the following statements are equivalent. Now, I wish I hadn't used a, because I usually use a for coefficients. This a is not a coefficient. But anyway, this is just some real number. These are all equivalent statements. If one of these are true, they're all true. X equal a is a 0 of the function f. Okay, what does that mean? Crosses the x-axis, right? F of x is 0 then. So if that's the statement, x equal a, that means that's the place where it crosses. Negative 16, positive 8, or whatever. Okay. Those would be the zeros of the function. If that's true, x equal a is also a solution to that polynomial equation. F of x equals 0, because that's what makes them zeros, right? Okay, we knew that. Here's the other one. X minus a is a factor of that polynomial. We know that because what did you do when you factored a polynomial? And it was equal to 0. When you factored this thing, and it was equal to 0, then you said this factor set it equal to 0, right? And when you did that, then you moved this to the other side, and you had x equal a. X equal a. Yeah, we've been doing that. That makes these all equivalent. And then this is the last one. If it crosses the x-axis, it's called the x-intercept. Those are your zeros. Those are your x-intercepts. Now, x-intercepts are always points, ordered pairs. A0. Okay? The y-intercept would look like what? Yeah, 0A or 0B, whatever you want to call it. Okay. Linear things, we always put B as the y-intercept. Yeah, whatever you want to call it. It's going to be 0 first. Okay. Because x is 0 at the y-intercept, y is 0 at the x-intercept. Got it. And if you know any one of these, you know all 4 of them. Okay? Make sense? Okay. Here's example 3. Find all the real zeros of that polynomial function. How would you begin? Say that, yeah, factor out a negative 2x squared. Sounds like a good move to me. What do you leave? X squared minus 1. Are you through? Why not? Okay, so this will be minus 2x squared. Don't forget that. That's still there. Now, I think you said have the right concept. You may not have used quite the right words. But how does that factor? X plus 1 times x minus 1. What we call that is the sum, the difference of 2 perfect squares. I don't know if that's what you said. It's not a perfect square. Yeah. Huh? Okay. All right. Now, what does this tell you? What do you do with that? We want to find the real zeros, so we set this equal to 0. Okay, we should have done that really first, but I was in too big a hurry to factor, okay? Or y'all told me to factor. Never mind. What happens? Set each of them equal to 0. So either negative 2x squared equals 0, or x plus 1 equals 0, or x minus 1 equals 0. Okay? What happens here? Divide by negative 2. And what does that give you? X squared equal 0. Okay, that didn't change much. And what would x be? X is equal to 0. Hang on to this a minute. What we call this is a double root. Okay? Because this would be either x equals 0 or x equals 0. I don't know if y'all saw the old, what was that guy's name? Bob Newhart show. One of his shows. He lived out in the country or in the inn or something. Had a neighbor, and the guy came in and said, there were always 3 of them. And the one that spoke to him, this is my brother Darrell and my other brother Darrell. Okay, this is my 0, that's my other 0. Okay, they have the same name, never mind. Okay, so that's a double root. Over here, what do we do? Subtract 1 from both sides, and that gives us x equals negative 1. Over here, we add 1 to both sides, and that gives us x equals 1. So we got 3 zeros. How many did we expect to have? Up to 4. But this is a double. So really we did have 4, only that's 1 twice. It's the same place, it's just twice. Yeah, okay. You won't always have that many, but you could. In fact, this one may have no zeros. This one happens to have 3. Okay. Now, it said find all the real zeros, then determine the maximum number of turning points of that graph. What would that be? 3. That would be the maximum. No guarantee it has 3, but it could. Okay? So, let's see. Okay? It crosses 3 times. But what it does, it crosses at minus 1. Okay, now here's where we use an end behavior. What's the end behavior of this? Okay, what direction is it? Down, exactly. So it's starting from down, and at negative 1 it crosses. And then at 0, and this is something you don't know yet, but you will soon. At 0, it touches, because this has what we call a multiplicity of 2. If it's an even multiplicity, it touches if it doesn't cross. An odd multiplicity, that's 1, it crosses, okay? And then it comes out and touches at 0, has to go back up because it has to cross again, because it's got to be going down, 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 positive 1. So yeah, you know exactly what it looks like. So it does have 3 turning points. 1 here, 1 there, 1 there. Because it has to be going down. See, the end behavior, the zeros, they work together. Now, the one thing they haven't talked about yet, and they really should, okay, is what is the y-intercept? That's so easy. It's 0 too. So 0, 0 is the x-intercept. This is 0, 0, and 0, 0 is also a y-intercept, okay? So it does cross at 0, both directions. It doesn't cross the x-axis, it just touches. All right. I think they'll probably draw it next, but let me erase my thought. We've answered all the questions that they said. Does anyone need this any longer? Okay. I don't want to erase it too soon. Okay, let's see what they do. To find the real zeros, we set it equal to 0. That's what I should have done first. And then, once we got it set equal to 0, then we factor it. And that's how the beginning of the factoring, removing the common monomial factor. And then we factor once more, and that's called factoring completely. Now, actually, usually for monomials we don't, but we could have said this was minus 2 times an x times an x times an y. That would have been a really complete factorization. But negative 2 is never 0, so basically divide that out or whatever. But the other two, x equals 0, x equals 0, that's why it's a double root. Okay, never mind. Okay, and then, so the real zeros are x equals 0, x equals 1, x equals negative 1. Because the function is a 4th degree polynomial, the graph of f can have at most 4 minus 1, which is 3 turning points. And just by my waving my arms, we showed that was true. They're actually going to graph it, and here it is. Okay, so we knew because it's even in and a negative coefficient, that's going down and down. That's the end behavior. So the first 0 it gets to is here, and that's a single 0, so it's going to cross there. The next one's a double 0, so it's going to touch there or kiss there and go back, okay? So it won't cross, okay? And the third one has got to cross, but it's got to be going downhill, so therefore we know it's going to look like this. 3 turning points, that's what we expected.
If it only touches it, is it still considered an x-intercept?
What's that again?
If it only touches it, it doesn't cross it, is it still considered
It's still an intercept because it does touch the x-axis. It crosses, touches, it hits the x-axis there, so it is an intercept. You're absolutely right. This interception, they ran out of bounds, and this one they turned around and got touched. No. Okay. This is Alabama. We have to talk in terms of football. Okay. Does that make sense? All right, that was example 3. Now, what we just saw in example 3, because that minus 2x squared only gave you 1 0, like I said before, x equals 0 and x equals 0, really it was 2 zeros but at the same point, we call that a repeated 0. Okay? So anytime you have a factor, x minus a, raised to the kth power, where k is greater than 1, that yields a repeated 0 of x equal a with a multiplicity of k. We had a multiplicity of 2, because it was x squared. X minus 0 squared. So that gave us that. Okay? When that k is odd, like 1, even 1, or 3, 5, 7, or whatever, then the graph is going to cross the x-axis at x equal a. But if k is even, 2, 4, 6, 8, 10, then it will touch the x-axis but doesn't cross at x equal a. It could be from below too. It doesn't have to be from above. It could be from below. It just comes up, kisses the x-axis, is a 0 there, and then returns in the same direction, either positive or negative. Okay. Now, they like to say k greater than 1. Okay, and yeah, to be a repeated 0, it has to be greater than 1. But these rules here hold even if k is equal to 1. And let me tell you what's happening there. if k is equal to 1, then it's going to cross. It's just going to cross, okay? That was k equal 1. K is equal to 2, it comes down and touches, comes down and touches. Well, actually, that looks like a straight line, doesn't it? K equal 1. Okay. This looks sort of like a parabola. Right there, it looks like a parabola, where k is equal to 2. If k is equal to 3, it's going to do this number. Sort of like a cubic function. If k is equal to 4, it's going to do this number. Hangs around just a little bit longer, like x to the 4th power. K is equal to 5, it'll even be longer, you know. Yeah, it only crosses at one point. And k is equal to 6, it would be, it just hangs around a little bit longer. They just get flatter and flatter, but only one point of intersection. Now this should be up there, that should be down there. Okay, but it's only one point of intersection. But what it does, the larger k is, the more it hangs around that point before it keeps going. But if it's odd, it's going to cross. If it's even, it's going to return in the same direction. Does that make sense? Any questions? All right. To graph a polynomial functions, then, use the fact that the polynomial function can change signs only at the zeros. And why is that true? Because polynomial functions have two characteristics. What are they? Continuous and smooth. Exactly. Okay? So, if it's a continuous smooth function, and it's going, as it said, use the fact that it can only change signs at its zero. Doesn't have to change signs at its zero. There's even multiplicities that don't change signs. But if it does, if it's a negative here and a positive there, guess what? Somewhere in between there it had to cross, because it's a continuous function. If it's positive here and negative here, somewhere in there it had to cross. Now it could have crossed 4 or 5 times, but it has to cross at least once. So that's what they're saying. If a polynomial function changes signs only at its zeros. Between two consecutive zeros, then a polynomial must be entirely positive or entirely negative. Because if these are your two zeros here, right there, and those are the consecutive zeros, you don't have any in between, it's either going to be like that or like that. Always positive, always negative in between. If those are consecutive zeros. If these are consecutive zeros, then here. If those are consecutive zeros, it's going to be like that. It's got to stay either only positive or only negative in between. Okay. Let's go back and look. This one. The function was negative here, positive there, had to have a 0. Okay. Now here it didn't change sign, but it still had a 0. That's okay, you know. And here, positive and negative, it had to have a 0. So the only times it doesn't is if you got a multiple and it's an even multiplicity of an even number, then it won't change signs. But that's okay. It still has a 0. It doesn't have to change signs at the 0, but if it does change signs, it's got to have a 0. Okay. What this means is that when you put the real zeros of a polynomial function in order, plot them on the graph, they divide the real number line into intervals in which the function has no sign changes. So if you have figured out all those zeros, like we had, say, a -1, a 0, and a +1, okay? We already knew the end behavior, so everywhere down here you knew it had to be negative. And this was multiplicity of 1, so it had to be positive after that. It had to cross it there. Okay, here we had a multiplicity of 2, so it had to touch there but not cross. So it had to be positive here, positive here. Here we had a multiplicity of 1. We usually don't say that, but we did. And so therefore it's going to change signs, but sure enough, the end behavior told us it had to be going there. So all this stuff has to work together. You can know a lot about the shape of a curve without plotting very many points at all. But what we did there, we split the graph into 3 sections. At each 0, we had a section. Actually, 4 sections. One left of -1, one between -1 and 0, one between 0 and 1, and one to the right of it. So you split the graph into intervals in which there is no sign change. The resulting intervals are called test intervals, in which you can then choose. If we hadn't thought through that, all we'd have to do then is pick a point in the test interval, like -2, and plug that in to see what it was. When it turned out negative, you knew it had to be negative. We already knew that from our end behavior. You could have picked 1/2 here, plug that in the function, found out it's positive. We know it's positive everywhere in between those two zeros. Choose a positive 1/2. We found it positive again. That told you had to come out careful. We knew that already because of multiplicity. And then we could chose +2. Found out that's negative as well. So you knew it had to cross there. We knew it did anyway. So all this stuff works together. Those are your test intervals. Pick a point in the test interval and determine the value of the polynomial function everywhere in that interval. Either all positive or all negative. Okay. They are skipping example 4. Let's do example 4. Actually, it looks like this is going to give us the most white space. Sketch the graph of f of x is equal to 3x to the 4th minus 4x cubed. Okay? Now, I'm going to go on and draw my axis, even though I'm not ready to do much plotting yet. I'm going to draw my axis there. Okay? Now, let me first ask you, and this is where I usually begin, what's the end behavior of this one? Both going up. So somewhere out here, this is going up, and somewhere out here, it's going up. Do you see why? Even exponent, the degree is 4, so that's even exponent, and positive coefficient is on the up and up. Right? That's what we did before. Okay. So that's just a little thing. What's the next thing we do? Second? Okay, find the 0, so we set it equal to 0. Okay, and then what do we do? Factor, and what can we factor? X cubed from all terms, and what would that give us? 3x minus 4, that's equal to 0. I can't think of any more factoring, can you? So what do we say about this? Either x cubed is equal to 0, or 3x minus 4 is equal to 0. Well, what does this yield? X equals 0, but that has a multiplicity of 3, which means it's going to do what? Cross at 0. We don't know which way it's crossing, it's going to cross. But we also know it's going to hang around 0 a bit longer than just a straight cross. Okay? How about this one? Add 4 to both sides. That gives us 3x is equal to 4. Divide by 3, and you get x equal 4/3. Oh, we love our fractions, don't we? Yes. Okay. Let's plot something. 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 1, 2, 3, 5, 6, 7, 8, 9. Positive 1, 2, 3, 4, 6, 7, 8, 9. But negative 1, 2, 3, 5. Now you see why I drew the x-axis down here? I knew it was going to be heading up that way. So I figured I wouldn't need as much down here. Now maybe I didn't put it in the right place, but let's go from there. So we got an x of 0, and that's going to be, when x equals 0, y is equal to 0. So that's going to be both our x-intercept and a y-intercept. Okay, and then x equals 4/3, that would be somewhere about right there. So there's a 0. Okay. Now I want to show you what we know. We know this has to be going up from here, right? Because its end behavior is up. We know this one has to be going up from here, but that is a crossing, not a hanging around. That's a crossing. This one's crossing, but it does hang around a little ways. So I basically can draw the shape of that curve right now, just based on what we know. In behavior, zeros, multiplicity of 3, so it hangs around there a while, multiplicity of 1 has to be crossing. It's going to look something like that. That's a pretty ugly, right? So let's use our intervals. We only have two zeros, so we have 3 intervals. So pick a point somewhere to the left of that first 0. -1. So let's plug -1 in here. F of -1 would be equal to what? 3 times -1 to the 4th power minus 4 times -1 to the 3rd power. Now you don't set it equals 0. That was just to find the zeros. We want to find out what number this is. What's -1 to the 4th? +1. So this is 3 times 1 minus 4. And what's -1 to the 3rd? -1. So this is 3 plus 4 equal 7. So at -1, 1, 2, 3, 4, 5, 6, 7. That looks like it's going, can I be that? I mean, I was lucky there. I came pretty close to it right there. So that's on its way up, okay? We already know that. Now let's pick a point between 0 and 4/3. +1. Okay, anyone do that real quickly? F of 1 would be 3 times 1 to the 4th minus 4 times 1 to the 3rd. That'll be a -1 because 1 to any power is 1. 3 minus 4 is -1. So it's down here at my, oh goodness gracious. I lucked out there again. Okay? Came awfully close to that curve. +1, -1. Okay, one more. Pick somewhere to the right of 4/3. 2. So let's do F of 2. And that would be, what would that be? 3 times 2 to the 4th power minus 4 times 2 to the 3rd power. Yeah, 2 to the 4th power. 2, 4, 8, 16. You just double as many powers. That would be 16 minus 4 times, say again, 8. Okay, so this will be 48 minus 32 equal 16. I was way off there, okay? 16 is somewhere way off scale here. It's going up here, so it's crossing there and going up really, really fast. Crossing here and going up really, really fast. And what we didn't get from that, but we could if we wanted to, we know because this is a cubic degree 3, multiplicity of 3, it comes out and hangs around. So you have this little jiggle here. It doesn't cross again, but it hangs around longer. This is just a straight crossing there. We got it. Now probably since this goes up so fast, this probably dips down lower than what I showed. Okay. But you got the general idea. Okay. If you look in the book, hey, look at that. Up to the left, up to the right, first thing we did, 0, 0, got those, and then did some test points, and sure enough, we are in pretty good shape there. Mine doesn't look just like theirs, but it's pretty reasonable. Okay? All right. Any questions on that? By the way, there is a checkpoint. I would definitely go home, go to the library, go to a classroom somewhere, do that as soon as I could. What's that? I don't know. I think it's around 8 in the morning, but I don't know for sure. Now, the Space Center is down on the first floor, I think in room 105 or somewhere like that, and SSS tutoring is on the second floor here, 212, I believe it is. Okay? And there's good tutors at both places. Can't guarantee they'll be there all day at both places, but the good tutors at both places. I know Brittany is there quite a bit. Just about every time I walk by, I see her. She's in one of my classes, so I know she's not there Tuesday, Thursday afternoon after 1:15, because she's in this class after 1:15, my physical science class. And I know Cameron does work study for me in the afternoon for not a long period of time, but a little bit. But if you arrange for them, and they have other tutors other than that, I just know those two are there and they're really good. All right, so let's move on to intermediate value theorem. Now, here's what we're talking about. Let's say we have a function. We're right now assuming polynomial function. That's what we've been dealing with. And we know at some point A, this function has a functional value of f of A. So that's going to be a point A, f of A. And somewhere over here at B, there's a value f of B. Okay? So there's another point on the graph. Okay? If these are 2 points on the graph, as long as f of A is not equal to f of B, if it is, you can't use the intermediate value theorem. But if those are different values, the y values are different there, if that's true, and most of the time that will be true, then for any number d in between f of A and f of B, there's got to be some x value c in between A and B. Why is that true? Because polynomial functions are smooth and continuous. The smooth doesn't matter here, but the continuous does. Okay? There has to be a number on the x-axis between A and B such that alpha c is equal to d. Has to happen. No way around it. Okay? In fact, most functions that will be true. Not all, but most of it will be true. Okay? Intermediate value theorem. Here's how we state it. Let A and B be real numbers on the x on the number line, x number line, such that A is less than B. If f is a polynomial function, so that f of A is not equal to f of B. Now here's how it could be equal. You know, a lot of functions do a lot of squiggling around. So if that one did, here f of A and f of B are equal. So you can't use intermediate value theorem there. But anywhere else, you can. Okay? Now, as long as f of A is not equal to f of B, then somewhere in that interval A to B, f takes on every value between f of A and f of B. If f of A was 3 and f of B was 5, then not just 4 is in there, 3.1, 3.2, 3.3, 3.00. Every value in between that. There is f takes on every value between f of A and f of B. And there will be some x between A and B where those values exist. The intermediate value theorem helps you locate the real zeros of a polynomial function in the following way. If you can find the value x equal A, at which the polynomial function, say, is positive, and then go a little bit further down to the right and find another value x equal B, at which is negative, you know there's got to be a zero in between the two. Now, even if you can't figure out exactly what that zero is, you know it's got to be in there. Okay? Then you can conclude the function has at least one real zero between those two values. They have 2, 3, or 17, but you know there's at least one. And the other way too. If x equal A is negative, and then somewhere that further down the way is positive, you know there's got to be at least one zero in between there as well. Okay, so that's how the intermediate value can help find additional zeros, especially those that are really hard to find. They are not factorable type zeros. So here's a function. You think you can factor that one? X cubed plus x squared plus 1? I can't. So if you can, lucky you. Okay. Now, so if I'm trying to see if this has any zeros, I want to evaluate a few places, like x equals 0. What's that going to be? 1. Well, you want to go right or left from there? Right, okay. X equal 1, what would that be? 3, okay. No guarantee there's a zero in between 0 and 1. So let's go to the left. Negative 1. What would this be? Negative 1 plus 1 plus 1, so that would be 1. Well, no guarantee there's a 0 because both of those are positive. So let's go one more to the left, like negative 2. This would be negative 8 plus 4 plus 1. That would be negative 5. Ding, 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 ding. You know there's got to be a 0 between negative 2 and negative 1. Right?
Would it not be negative 3?
Second.
Would it be negative 3?
Okay, we picked negative 2.
I know negative 8 plus 4 would be negative.
Oh, okay.
Plus 1 would be negative 3.
Okay. Well, this would be 5. Negative 8. Yeah, you're right. Okay. Plus 5. Yeah, I was doing plus 2. Yeah, plus 5 would be negative 3. But anyway, it's negative at negative 2. It's positive at negative 1. So you've got to have a 0 in between there. You don't know where. Here is negative 2, negative 3, like we said. And here is negative 1, 1, like we said. So you know there's got to be a 0 in between there. So what do we do? Well, what I would do was pick a value in between there, like negative 1.5. Plug that in, see what you get. If that turns out negative, you know it's got to be between those two. You pick one between that. You keep going until there was an old guy named Archimedes. Have I told you about him before? Okay. He was trying to figure out the area of a circle. That was hard to do. But he knew what the area of a square was. So he put a square just outside a circle and just inside a circle. Figured those two areas, averaged them, got pretty close. Then he figured out, he was a real sharp dude, he did a pentagon inside and outside. Averaged those, and they got even closer. And then a hexagon, and then an octagon, and then a decagon, and then he just kept going larger and larger. All those that had regular things, he could figure, split them into little triangles, and he could figure the areas of those, inside and outside. And finally he said, okay, that's close enough. You know what he called that method? The method of exhaustion. He got tired of doing it, so he just stopped. He said, that's close enough. So you can keep doing that as long as you want to. Just pick a value like negative 1.5, if it's down here. Then pick a value like negative 1.25, it might be up here. Pick a value in between those, negative 1, Just keep going until you say, okay, that's close enough. You'll get closer and closer to 0, so forth, and say, okay, I know it's somewhere close to that. So that's what you do. So it follows from the intermediate value theorem that f must have a 0 between that. I've just given you the procedure. Okay, I take it that we must be running out of time. So let's, this just says the same thing. Continue that line of reasoning. You can approximate any real zeros to any desired accuracy. It just depends on how tired you get. Okay, so example 6 will be where we pick up next time. Okay? Homework exercises. I would do all of 9 through 14, but the answers for the odds are in the back, 9 through 13. But I would do them all just to get used to the concept here. Then do either 15 or 17. That would be fine. Any of the odds 19 to 29. Any of the odds either 31 or 33 or both. Any of the odds 35 to 49, either 51 or 53 or both. Try doing any of the odds 55 to 63. Those are a little bit different, but give them a shot. Any of the odds 65 to 73. Any of the odds 75 to 87. Either 89 or 91 or both, and stop there. We'll do the rest of those next time. Good deal. Any questions? All right, have a good weekend. Of course, that will be doing lots of math. That'll make it good, right? Work on those papers. If you haven't turned in those first quizzes, get me those quizzes. And if you haven't finished the test, raise your hand. Okay. What's that?
What do I need to come take the test?
Anytime during my office hours. In this room, you mean? Or, if I'm in my office hours, I'll usually find a room somewhere close to my office, so you don't have to far to walk around and stuff. When do you want to do it? Today, tomorrow? Huh? Today. Now tomorrow I'm on Birmingham campus, if that's more convenient for you. Huh?
We got a game.
You do? Okay. At home or away? Away sucks. I was going to go see it if it was home. Okay. All right. So you're going to do it today? Okay. Today my office hours are between 10:45 and 1:15. Are you free anytime in there? Okay. Are you free right now?
No, I got a class.
You got a class now.
I should get out there.
Today you said 10:45.
To 1:15.
So about like 10:45.
Okay, right around 10:45. I'll still be up here right at 10:45. Sometime after that, I'll be heading to the office. So check here in technology. You know where my office is? Okay, 265. Let me show you. You go out the door here, take a left, go down that half flight of stairs, go all the way, almost to the end of the hall, the last office on the left, right before the stairwell across from where everything goes down to the stairs. Yeah, down this step right here, to the half flight of stairs. And then you go down until you walk up into the wall, okay? Before you get to the exit sign, that door right there, 265. It's right next to the mechanical room, so it has doors like this, right between the stairwell and that. Okay. What's that?
Yeah, I was wondering, can you pass my information on to the list of meeting things? What's both of them, really? They can reach out to me.
And what?
Can you pass my information on to the tutors so they can reach out to me?
Okay. Well, usually you go sign up at the place. I think, I don't know how it works. I think that's what you do. SSS, you go sign up at T12 or Space Center, I'm sure you do the same thing there.
Okay.
105, I think it is.
Okay.
Down on the first floor.
Okay.
Tomorrow, you know where Dr. Pruitt's office is? Okay, I'm in the back of his. When you walk in his office, the secretary's sitting right there. Behind her is a copy room. That's where
And you're gonna be there all day tomorrow.
I'll be there from 7:45 to 1, unless they call a meeting or something. So I don't know if they're going to do that. I haven't heard one. But if they do, other than that, I'll be there. What's that? Space. Okay. Let me sort of give you. Okay. Actually, they're really not far apart.
You like campus?
Man,
You like campus?
look at this.
You ought to be tutoring math, are you?
Why are they doing that?
Because you're good at it.
I don't even know how to do it.
What? You know, 090, 098, 100, and
I
112.
didn't have those classes yet.
No, you already know them because you exempted out of them. You've had 112, right? And I think
I
you've
had
been passed.
AP calculus in high school.
Okay, that's why I say you should be tutoring math. Yes.
I already have a job.
Okay.
I go to school Tuesday and Thursday. I work Monday, Wednesday, and Friday.
Okay. Yeah.
I
You
have
don't.
a full schedule.
Yeah, I understand, but I want to give you a hard time. Is that okay? Okay. Good.
Tutoring's not my thing.
Huh?
Tutoring's not my thing. My dad's